people are saying that everything in it is cloud, but the question is, what is the cloud? So for me, cloud is very concrete physics, cables, fibers, connectors, and all of this stuff. So I'm happy to be here. My name is Robert Bondarenko. Normally the extension would be infinera.com, but since 1 month is already nokia.com, so I'm part of the bigger family. But basically what we are doing and partnering with Clico here is supplying the solutions for data center interconnect, meaning getting light to the fiber and connecting lots of traffic in a reliable way through that. So when we are seeing our predecessors with the presentation, they were saying that there are lots of high capacity ports and they are really growing. And the driver for that is, of course, artificial intelligence, even in the cars. So the Meta was saying last year that the average year-to-year growth of the traffic was 100% because of the artificial intelligence. 2 years ago, we met on the ECOG the guys like NVIDIA, guys which were never there, right? So because the people perceive that the server which are specialized for the video, for this kind of applications, are getting more and more traffic. So we see that the traffic demand, the speed of the ports is driving also the necessity to move the parts from the electric to the optical. So Infinera is kind of pioneer of integrated photonic circuits, which basically is combining several lasers, amplifiers, and so on in the kind of photonic silicon. And with this, we can achieve high capacity on very small footprint with small energy. And we were using these innovations for the long haul, for the subsea transmission, and still we are the best in that area. But we also deployed this optics into the plugs, so you can buy now the coherent plugs that you can put into the routers, into the switches. So there are few specialists in the world manufacturing those plugs. I will say something about it in the next thing. So basically, optical is the physical media of connecting all of the cloud stuff, all of the applications, and needs to be done in a reliable way. And I will be trying to tell something about the details what we are doing here. So when we are talking about the data center interconnect, it's basically interconnecting the data centers. Usually it is point-to-point, but as the reliance requires, often the guys like the Metas, Googles, so they require that it's not only point-to-point, but it should be 2 paths, there should be 3 paths, there should be 5 different routes connecting the data centers. And it's not only 2 data centers, but it could be many. So actually we are coming to switching of the traffic, to coping with the physical distances that they are different. You have different delays, the things that you need to cope with the physics. So we have the application when the data center is connected 10,000 kilometers through the subsea going around the Asia, Pacific, or Africa, because nowadays it's kind of easier to make the subsea cables to connect the world than going to the terrestrial. But we have also, of course, the application on the terrestrial, and those optical engines are used in both of those things. When we are talking about the connecting the data centers, then we have several ways of transporting the traffic on the longer distances. So one thing is embedded laser built into the device, into the transponder of the WDM system, which is specialized for coping with the long distances. It's having several ways of line code to cope with the distortion of the optical transmission. It's having higher powers, it's having width channels, and these are the stronger ones. So currently, the lasers that they are built on the blades of our systems that are shown here are of the speed of 1.6 terabit, which is actually 2/8 of 800 gig, and we are just launching the transponder with 1.2 terabit. To cope with the longer distances, actually we came to the channel limits. So if you want to have higher throughput of the wave, then you are actually needing to have more and more bandwidth, more and more terahertz. So if we have 400 gig transmission, then it's, I don't know, 75 gigahertz. If it's 800, then we need already 120 terahertz. If we want to have 1.2 terabit, then it's 150. So those channels are getting wider, and the speed is higher. So actually, either you got higher channel, but it's wider. You cannot cope with this channel limits. So therefore, we invented something that it's called Super C and Super L. So we extended the bandwidth of the fiber. So we manufacture the ROADMs, the amplifiers, the lasers that they can run in the bigger frequency spectrum than normally standard 80 or 90 channel systems. So this is allowing to add 20% of additional capacity to the fiber. So this is, we are number 2 market share, and maybe that's the good moment of mentioning why we are now part of the Nokia family. So Nokia company is known for many years with the Bell Labs, with the cloud, with the 5G, with the GPONs, with the WDM systems, with the cloud, with IP, with everything, right? It's a huge company with lots of history and lots of future. Although the speed of developing the new things, we were a little bit more advanced in the photonics. So Nokia decided that they need to speed up the portfolio in the high speed and also in the optical components. So with this, both companies agreed to merge together. The model of the merger was that Infinera shares were replaced by the Nokia shares. So actually, the Infinera company is now having the new owner, which is Nokia, and now we are integrating all of the operations alongside. So you will see now more of the Nokia logo in respective of activities for the data center connect, and you will not see the Infinera logo. So the reason for that is that the 32% of the market share of this high capacity connectivities was supplied by the Infinera. So for the Nokia, this is actually addressing the big market that Nokia was not there. And that's mainly American market, that mainly the hyperscalers, and that mainly those devices that are based on the photonic integrated innovation of Infinera. So not only we are building this kind of small devices that in the 4 rack units, it's 6.4 terabit of the capacity, but we are also implementing this photonic integrated devices on the plugs. So the plugs is having those beauties that actually you can have specialized guys for the IP, like the Junipers, Aristas, and they don't need to be so specialized in the coherent WDM optics, but they can still get the plug, put the optical plug into the system, and to cope with the longer distances with or without amplification, with or without multiplication of the multiple channels in the WDM spectrum. So it's common ZR Plus standard that it's commonly used already in the industry. So we are manufacturing those plugs that are ZR plugs for the third-party devices. And so we are using them to optimize the cost of the lasers for our WDM and our IP stuff. But also those devices, those plugs, QSF PDDs, is possible to put into the router, right? So those routers or switches that are capable to use the standard of the ZR Plus, they can use the Infinera plugs and deliver the transmission over the WDM on the longer distances and longer speeds. If I'm talking about the plugs, so classically there are 400 gig plugs that they can be used on the lower speeds, like 100, 200 gig. The beauty of those plugs that we are manufacturing, that's making us a little bit differentiate from the other vendors, is that the 400 gig signal is made in the subcarriers. So actually it is constituting of 8 subcarriers, and each of the subcarriers can be controlled independently. So this is giving the possibility that the 400 gig coherent optics could be used for the single fiber operation. So if you have a fiber pair, that's normal things, but more and more you can also utilize the application when it's just one single fiber available for the delivery of the transmission. That would mean that the 400 gig signal is divided in 2 signals, 200 gig left, 200 gig right, and we have just only single fiber bidirectional transmission. So you can imagine that lots of networks are, for example, using the GPON. GPON is also single fiber infrastructure, right? And it's kind of locked because it's sharing kind of spectrum of the frequencies that are shared among multiple users, and they are connected with these passive splitters. So with this approach, we can get the frequency in the place of the spectrum which is not used by the GPON, and we can make on the same infrastructure, on the same single fiber with these passive splitters infrastructure, we can provide 200 gig transmission point to point for the dedicated users. So this is fantastically enhancing the possibility of reaching the customers. And you are experiencing yourself that the data centers will be located closer. There will be much more of the data centers. So actually, this GPON infrastructure, which was fantastic for the higher capacity, but that was yet locked to the higher speeds, is actually being now open for this kind of transmission. So we are very, very happy with this kind of cooperation now also with the Nokia, that it's, the GPON is the bread and butter for them. But on the same GPON infrastructure, we can run 200 gig coherent single fiber transmission, I don't know, for the data centers, for the mobile stations, and so on and so forth. This year we are launching the plug, which is capable to run 800 gig transmissions, right? So it is showing that this optical thing is delivering high capacity, but it's less power hungry. So when we saw all of these expectations for the data centers growing, so one thing is, of course, everybody is happy that there's more and more traffic, but behind it, it's more and more devices, more and more power, and each of the connections between those devices is consuming the power. So the optics, the laser light is something very well suitable for achieving high capacities and lower power. So we are now putting on the market the 800 plugs that then can be fed into the routers, switches, and the servers, and so on. We are making the version which is stripped out of the digital signal processing and things like the single fiber for the intra-data center. So actually the short distances between the servers. So we are also opening this kind of release of the plugs or actually components that are available for the server manufacturers, so they can use this technology for connecting the servers. And we are working on the next generation for the plugs which will be capable to run 1.6 tera. Actually, then you can imagine actually what the coexistence of the optical and IP world we are talking here. And of course, it is a question how to control those devices. So it's usual conflict about, okay, the guys from the optical physical cables and from the IP. The guys from the IP, they believe that it will be somehow connected. The routers will find each other and they will be connected. The guys from the optica and the cables, they say, well, it is not so simple. There are actually physical plugs, connectors, and the routes that needs to be observed. And of course, it is necessary then to monitor, to troubleshoot those kind of networks. So if we are putting now the WDM plug into the router, then we are actually demanding from the personnel of the IP that they will be understanding the physics of analog optical transmission through some media that it's can behave in very ways, depending also how mixing different signals. So it is a challenge. But as those plugs are intelligent, I mentioned that they're capable to run the single fiber. You can run on this also the encryption, but those plugs are also talking with each other. So actually they can work in the point to multi-point configurations that you are putting, I don't know, one plug which is 400 gig into the router, then the passive splitter and the 4 different plugs that on the subcarriers will be actually aggregating the traffic from 4 different devices to one port physical on the router. So this intelligence is in those devices, but this intelligence is also allowing us to talk to those plugs, also to receive the data, to control the frequency, to put them in the WDM channel at the beginning of the spectrum or at the end of the spectrum. So actually we can remotely control those optical parameters with the special software, even having the situation that this plug is sitting in the RP router that does not understand WDM and this kind of specifics, right? So this is something that is allowing us then to build really high capacity and flexible applications. So some examples about the potential topologies. So this is an example of the laser that is built on the blade. It's specialized, heavy duty, 1.2 terabit modulation, Super C and L. So we have 11.6 terahertz spectrum for our usage. So we can achieve on such a connection more than 90 terabits end-to-end connectivity. Of course, if the path will be longer, then we are losing on the error corrections and so on. But basically, this is what is possible to achieve from the fiber pair nowadays. If we will be putting the plugs, the coherent plugs into the transponders, then we can achieve the, then we are talking about the C-band and super C-band, which is having the lower terahertz. It will be shorter distances, but cost optimized. And the same, we see that we can now also put the 800 gig plugs into the third-party devices. So actually, the topology will be looking like we are putting the plugs into the IP devices. Then there are filters, multiplexers on optical, and we are connecting the places. So these are the few models that you will see in the next years, how the data centers will be interconnected. And it's also a question, okay, it's very complex, it's very a critical amount of the data that we need to make sure that it's connected and it's replicated in real time. And at the end of the day, we are talking about the physical paths of a few hundred kilometers through different territories. Sometimes it's a sea, sometimes it's a land, sometimes it's aerial cable. So there are lots of things that can potentially influence. So of course, we are building then the redundant paths to allow the possibilities of connecting the data center with different routes, with different systems for the resilience. So the replication will be happening even if a few of the paths will die. But still, this is kind of basic, right? So if line is breaking, then switch to another path, or the capacity is doubled or tripled. So you have the kind of spare capacity to put the traffic on the different paths. But sometimes it's not so easy. So actually, you don't know why there is a situation that that you see the distortion if the traffic communication. And for that, we have implemented on the open source the possibilities of streaming telemetry. So normally it's the management system that is actually asking the devices for the data, correlating those data, triggering the alarm, visualizing this, and so on. This, of course, requires extra communication, and it's kind of snapshot of the individual moment. But when we are seeing the physics, the influence, I don't know, of the weather, of, I don't know, rails going over the cables, and many different things, like the float of the traffic and so on, then it's kind of a challenge to find the root cause why this transmission was deteriorated, where we have problem, why we have this problem on Thursday evening every, I don't know, second month. So it is good to collect then the data. So one of the software modes in all of the devices that I was presenting here, and it means the embedded optics, the plugs that we are putting into the routers. They have a possibility to actually deliver the performance data in proactive way. So in the 2 minutes interval, we are defining, okay, which of the data you need to supply to the collector. We are using the open source that it's actually collecting this data, storing this data, providing the graphical visualization and correlation with other systems. So then the troubleshooting is much easier. So you saw many advanced tools for the Juniper, for the Aristas, actually to troubleshoot, to see how the performance of the cluster is behaving. But with this, you have also this physical part. What is actually additional information? What was happening as an interconnect on those lines, to make sure that you are addressing really the root cause of the situation. So when we will be talking about the I6, the 800 gig transmission, then we can collect the data regarding the transmit power, the receive power, the bit error ratio between the before error correction. We see the quality factor. We see the OSNR figures. So we can correlate those facts with the things that we have from other tools, and we can say, hey, we see, okay, on this date, we have deterioration of something, right? So we can put then, I don't know, reflectometer, we do the analysis of the fiber, but we have actually very precise moment of if it's regular or not, what is happening with the transmission. So we have this possibilities to read those details from the lasers which is built, but also from the plugs that we are putting into the routers. So this is actually this extra software that is running on the plugs independently from the routers. It could be tunneled through the VLAN into the router, but it could be also separate devices that is collecting the information on the laser side. And we can read the same from the plugs, from the ZR plugs, which are in the third-party devices. So we can have those optical statistics. Again, here's the power levels, transmit, received, the same things that you show on the high advanced transmission device. The same is available on the plug, on the software that is sitting on the plug. As I was mentioning also about the line systems, so often the data centers are connected in multiple shapes, in the triangles and pentagrams, not only point to point. So sometimes you have just two paths and so on, but you can actually see all of the waves that they're running of this signal and see, okay, I don't have problems on those channels, but I have problem on this channel and in this time, right? So this is additional information that is available, and of course the things like the performance of the control units, the memory usage. So all of this data can be correlated to make the troubleshooting easier. So yes, we are depending big time on the data center. We need to accept that those will be in the common cloud, in the public cloud, in the private cloud. They will be interconnected, and it, of course, will be very sensitive data, and very much depending on all of the providers to make sure that they are reliable and available all of the days in the year and all of the seconds. So with this, we trust that the development that we did on the physics, on these optical components, on the lasers, on the line systems, but also on the tools for the monitoring, will allow the possibility to build the solid ecosystems of the data center. And if you'd like to know more, I'm inviting you to the booth or to the clicker, and wish you good tea and coffee.